And I would like to thank the Chemical Engineering News for this great honor, and also all the nominees and sponsors, and I would also like to congratulate all of the other awardees. It's really a pleasure to be among these bright scientists. So I would like to tell you today about how imagination can spark creativity in polymer science and play a role in our modern technology as well. So I will begin with my journey. I'm actually from Damascus, Syria. So Damascus is actually the oldest capital in the world. So it's one of the oldest inhabited cities in the world. It's 9,000-year-old city. So I'm really I feel really privileged to have been raised in that city. I also obtained my bachelor degree in chemistry from Damascus University back in 2005. And then I also feel lucky that I lived in different countries and very diverse really skills through working in different application areas, like in synthetic organic chemistry during my master's in chemistry at King Fahd University in Saudi Arabia, and then also working on supramolecular polymers and nanomaterials for bone fracture treatment during my PhD at the University of Alberta in Canada. And then I worked on porous polymers for water purification during my postdoctoral studies in Will Dachtels lab at Cornell University here in the US, which I will tell you a little bit about later in this presentation. In Arkema, I worked on acrylic radical polymerization, which is actually, I was actually part of a team that developed the first recyclable wind turbine blade plastics, which is now a commercial material. Unfortunately, I'm not going to have a chance to tell you about this cool work today. And also, currently in DuPont, I'm working on polyurethane polymers for semiconductor chip fabrication, which I will tell you more about later in this presentation. So as can be seen from my journey through working in different application areas like in health, water, energy, and electronics, I acquired very diverse skills in different fields of chemistry. But more importantly, living in different countries has provided me with really some important soft skills, like the courage to work in new areas and learn new skills, the ability to think creatively and out of the box all the time, and also the ability to adapt quickly in new cultural and new research environments. And more importantly, I have very rich imagination that allows me to think unconventionally. I actually consider imagination is the most important skill needed for scientific research. And today I'm going to give you two examples from my journey about the importance of imagination. One during my postdoctoral studies at Cornell, and the other is in my current work in DuPont. So I will get started with the first example from my postdoctoral work, in which imagination inspired a breakthrough in water purification. So I would just would like to give you a little background about the emerging water contaminants. These are organic micropollutants that we use in our daily life, like pharmaceuticals, personal care products, pesticides, and many other categories. There are thousands of these molecules. I'm just showing a few examples of them here. But there are thousands of these molecules that have been found in surface and groundwater supplies. And the challenge with them is they are not being removed effectively by current water treatment methods. And many of them have adverse health and ecological effects, especially like PFAS, for example, type of pollutants. So to address this global challenge, researchers over the past century have explored a variety of polymeric adsorbents, and among these are beta-cyclodextrin-based polymers. And the reason for that is because beta-cyclodextrin is really a sugar. It's derived from cornstarch, so it's really sustainable material. It's really attractive from that perspective. And more importantly, it has unique cup-like structure that you see in here, the stereo structure of it, that enables it to form host gas complexes with thousands of organic molecules in water. So because of these really unique features, basically researchers made hundreds of different polymers of beta-cyclodextrin for water purification. I'm just showing an example of them here, which is called the epichlorohydrin cyclodextrin polymer. It's one of the most famous ones. Now, the challenge with all of these previous polymers is all of them have very low surface areas. They are basically non-porous. And as a result of their low surface area, they absorb pollutants very slowly over hours or even days. And actually, looking at literature, I really discovered that the reason for their low surface areas is either the use of acyclic flexible crosslinker, like epichlorohydrin, for example, or actually a linkage that's like long or relatively kind of flexible linkage, like amide, ester, or even carbonate. So I actually decided to fill this gap, and I wanted to develop the first high surface area cyclodextrin polymer for rapid water purification. So The inspiration actually for my idea came from the bricks game, which I used to play a lot when I was a child. I was really inspired that in order to have a high surface area cyclodextrin polymer, we need like really rigid building blocks of non-complementary shapes, exactly what you see in the bricks, that pack inefficiently to form a network with permanent voids, again, like what you see in this image here of the bricks. So I put 4 criteria for the crosslinker that I was searching for. It needs to be structurally rigid and also linked with beta-cyclodextrin by a short linkage and a rapid irreversible reaction to enable frustrated packing and kinetic trapping. So basically, I choose tetrafluorotethiionitrile as it satisfies all of these conditions, and it can react with beta-cyclodextrin by nucleophilic aromatic substitution reaction. And I developed this one-step polymerization reaction between the 2 monomers using these very simple conditions and a cheap base. And I was able to get the first high surface area cyclodextrin polymer. The surface area is around 250 square meter per gram. And as a result of that, this polymer can sequester thousands of organic molecules in water almost instantaneously, like you see in the blue trace here, in just a couple of seconds, unlike the commercial water filters based on activated carbons or even in previous beta-cyclodextrin polymers, which take much longer time. In addition, this polymer can be recycled several times using very simple conditions at ambient temperature. So this imagination-inspired work really led to a new line of research in Will Depter's lab, and several students continued this work and built on it, and they really developed several new versions of this polymer for water and air purification. And in addition, this polymer also inspired many researchers around the world, as our original report in Nature got cited over 1,000 times in less than 5 years. And also we had several high impact publications and also granted patents worldwide. So this work also laid the groundwork for a startup company called Cyclopure, which was chosen by Chemical Engineering News as one of the top 10 startups watched in 2019. And also it currently commercializes several products for water purification. So this really shows how imagination can be really impactful, and it can really help us solve some of these societal problems that we currently have. I would like now to switch gear and tell you about the second example in my current work in DuPont, in which imagination plays a role in electronic chip fabrication. So as we know, electronic chips are the heart and the brain of the different electronic devices that we use in our daily life. Really, they are an essential part of our modern technology nowadays. Electronic chips are made on silicon wafers that you see in the bottom left. Each wafer contains hundreds of chips, which are diced after the fabrication process. Now, if we magnify and look closely at the surface of these chips, we can see the actual circuitry containing a very complicated network of interconnected micro wires of different metals, and also semiconductor features, which can be as small as like a few nanometers in size. If we look at the cross-section of the chip, we can see multiple layers of like different metals and semiconductors. In some cases, we can have as many as 30 layers in total. Now, each layer must be completely flattened before we deposit the next layer. This flattening is made by a process called chemical mechanical planarization, or CMP. So basically, different CMP processes are applied throughout the chip fabrication process. So just to show how important CMP is, so if you look at this top right image, that's where if you try to make the chip without CMP, basically you get a useless chip. You can't use it for any device. It cannot really function. CMP is really what enables us to really accurately print the microscale features on the chip, and really it's essential to modern electronics. Here's the CMP machine and the 5 main components of it. The wafer is actually mounted, actually facing downward on the wafer carrier head that you see in there, and is pushed against the polishing pad. Now, both the pad and the wafer rotate in the same direction, but at different speeds. And also at the same time, a slurry is dispensed through the slurry dispenser. Now, the slurry is a chemically active solution that contains abrasive microparticles. Now, the chemical activity of the slurry enables the chemical polishing, whereas the abrasive particles and the polishing pad enable the mechanical polishing. Also, we have a conditioner that's pressed against the pad to create a rough surface texture to enable the mechanical polishing as well. Actually, DuPont is one of the industry leaders in high-quality materials for CMP, especially polishing pads and also slurries, and it continues to innovate to meet the new industry needs. Just to appreciate the complexity of CMP and the importance of imagination in this process. Here I'm showing the total number of variables within each of the 5 components of CMP. You can see how many variables we have, and there's also large space within each of these variables. This process is extremely complicated and it's not well understood. Any variation within any of these variables can impact the interfacial processes between the wafer, the pad, and the slurry. You can see at the interface also the slurry abrasive particles in blue, and also these features on the pad, which are called the asperties, and they are created by the conditioning process. They are in the micron dimensions. Now, the chemistry and the physics at this interface, like the hydrodynamic state, the friction, the shear layer thickness, or the contact area, and other phenomena as well, dictate the polishing output parameters in each of these 6 different categories, which are also very complicated, and it's very difficult to balance all of them or even deconvolute them to achieve the desired performance in all of them. So that's why imagination is really essential to visualize and hypothesize how and which input variables can impact the interfacial processes, and how the interfacial processes impact or dictate the polishing output parameters. Imagination is really the core and the driver of our research in CMP. By the way, the polishing output parameters not only influence on the efficiency of the fabrication process, but also on the semiconductor, on the performance of the semiconductor itself. So now I would like to zoom in into CMP polishing pads, since my research focuses on this area. CMP pads are made of polyurethane block copolymers. As we know, polyurethanes are very versatile polymers, consisting mainly of 3 parts. So we have the polyol chain in red here that aggregates randomly to form what's called the soft segments. And we have the cyanate in blue and the chain extender in green, which co-crystallize to form what's called the hard segments. Now, the choice of these 3 components dictate the thermomechanical properties and the viscoelastic properties of these pads. In addition, we can have also multiple components within each of these categories, like more than 1 polyol or more than 1 chain extender. So the formulation space of CMP pads is huge. And again, that's why imagination is also really important to correlate between structural like variations and the resulting properties of this pad. In addition, also we add blowing agents to create pores in the pad. So basically, CMP pads are hard forms, and you can see on the right image that we have also different grooving patterns and designs. So different pads also to meet a wide variety of application and performance requirements. Just here to show quickly how we do research in CMP pads. So we begin with ideation and hypothesis. Imagination actually is really the driver to ideation and hypothesis. We imagine how and which input variables can help us achieve the output parameters that our customers are looking for. And then we proceed to more advanced steps like DOE design, formulation screening, making or evaluating even the polishing pads, and then re-evaluating hypotheses if we need. Once we identify promising candidates, then we proceed to more advanced steps like scaling up and customer sampling. So imagination is really the driver of our research in CMP pads. I'm not going to dig further into my actual research in the point, but I'd like to say that actually a new family of pads that I co-invented is expected to go to market next year, which I'm really happy about. So I would like to end my talk with a really nice quote from Albert Einstein, which I really believe in. I think it's really important message about imagination. I'm going to read it out loud. Imagination is more important than knowledge, for knowledge is limited to all we know and understand, while imagination embraces the entire world, and all there ever will be to know and understand. I think this is really powerful, and it really shows how important imagination is in scientific research. So keep imagining. At the end, I would like to thank the key influencers around my, my journey. I really thank all of them. From each of these great people, I learned at least something that contributed to who I am now. So I thank all of them for their input, for their contribution, and for their guidance along my way. And I would also like to thank my family, my wife, my 2 kids, for their support. And also, I would like to thank all of my colleagues along all of these stages. So also for their help and support throughout my work and my studies. And I would like to thank you for your attention, and I can take any question now. Thank you.
Thank you so much, Aladdin. I wanted to ask you, you've worked on like a really broad range of problems, and I was wondering, how do you approach a problem in an area that you're unfamiliar with?
So the first thing, so if the area is really outside my expertise, I start with books. So it's really great. So I usually choose books that are kind of not older than a 2-year-old, maybe. I try to read recent books about that particular area. And then I go to usually like review articles, because review articles are really great overview of the fields usually and the recent advances in it. And then I go to research papers and dig further and further into kind of the most recent advances in that particular area. These are the steps that I usually take. If the area is not that far from what I know about, I start with reviews, not books, basically. But for example, when I worked on polyurethanes in DuPont, I start with books because semiconductors were very new to me. Polyurethane, I've never worked on polyurethanes before, so I start with books. So that's a particular example. Yeah.
All right. Well, thank you so much, Aladdin.